Hi, everybody. Hopefully, you had a chance to finish off the tests and get all your assignments in. I'll get those graded shortly. We'll talk about them on the next office hours, or you can also send me questions. The key will be posted for a while. We jump forward a couple chapters at this point to chapters 13 and 14, which involve vibrations, waves, and sound. You've all dealt with vibrations before. You've seen it in a lot of different ways. The type of vibrations we're going to be talking about in this chapter are simple harmonic oscillators, which undergo simple harmonic motion, or SHM for short. Simple harmonic motion is really quite critical in the production of any kind of oscillations or clocks or even musical instruments. They're also involved in almost every kind of physical medium. And let me get into this real quick. Periodic systems are any systems that repeat on a regular basis. For example, the rising of the sun, change of the seasons, tides, bird songs, rotation of a bicycle wheel. Just a quick reminder or some notation on this. Period T is the time required for the oscillation to repeat itself. Remember, we used period before for an object going around in a circle. The period was the time required to go around once. The same thing's true with periodic motion or oscillations. The time required for it to complete one complete oscillation is the period, capital T. You can also measure the period between two crests, or in this case, where it goes down across equilibrium, or you can measure it between any 2 points where that repeat occurs. Here it is between two troughs. Couple definitions. Simple harmonic motion, the one we're talking about, is periodic motion whose motion is in the form of a sine, cosine, or e to the x curve. It turns out almost all of the oscillations we deal with in everyday life fall into one of those categories, or some combination of those. The single requirement for simple harmonic motion is that the restoring force, that's the force that's trying to push it back towards equilibrium, is proportional to the displacement of the object. Mathematically, this would be equal to the force is equal to negative some constant times the displacement delta x, negative sign indicating that the force is against the displacement. But yeah, you're right, we've seen it before, Hooke's laws for springs. So what does this mean? Anything that obeys Hooke's law is a simple harmonic oscillator. Now, a couple quick definitions before we get started. Down here on this graph, if I can find it, whoops, these points right here are called the crest of the object, and these points down here are called the troughs. And I just discovered my regular pad is not working, so please forgive me as I write these out slowly. That's crest. These are the troughs. Oh, gracious goodness. And I just forgot how to spell it. I'll leave that out. And this line right here represents the equilibrium point. This is the point where it tries to return to at every single oscillation. This is the point where there is no force on the object. So the further you move it away from equilibrium, in this case, there's a restoring force that's trying to push it back down this way. If you push it this way, there's a restoring force that tries to push it back this way. At equilibrium, the force is equal to 0. All right. All spring systems can exhibit simple harmonic motion. A guitar string is a spring. It exhibits simple harmonic motion. A piano string. Even the air inside of a woodwind exhibits simple harmonic motion because the air gets compressed and it acts almost like a spring. Oh, maybe I do have these. Oh, a few things on it. Whoops. Couple of quick definitions. The distance between the equilibrium point or line that I drew before and a crest or a trough is called the amplitude. And we usually just abbreviate it with a capital A. And it's equal to the maximum displacement of an object. The period is the time required between two oscillations, and we usually represent that with capital T, and it's measured in seconds. There's also the other interesting unit in this chapter we're going to use a lot is frequency, F. It's the inverse of period, and its number of oscillations per second. Its units are 1/seconds or hertz, and so they're directly related. So for example, if the period in this particular case is 2 seconds, the frequency would be 1/2 or 0.5 hertz. What does this mean? It means that it takes 2 seconds for this thing to complete one oscillation. And the frequency, how many waves per second? Only 1/2 of a wave passes by a point each second. So ideal springs. So remember again, for an ideal spring, K is the spring constant, and the negative sign just indicates that the displacement and this restoring force is always in opposite directions. That's what that negative sign there means. So relaxed position, there's no displacement, and so the restoring force is 0. If I compress the spring this way, so my displacement now is pointing this direction, that's delta x. My restoring force is back towards the center, and it's equal to K times x, or its magnitude. If I stretch on the other hand, in this case delta x is pointing this way, the restoring force is opposite in its direction, and its magnitude again is equal to kx. And it's technically negative because it's acting in the negative direction. Now, what happens, and this is one thing we haven't worked with springs before, what if you put two springs side by side? So take a quick look at this. In this example here, I place this one mass, excuse me for a second, changing spring color or colors here. If I place this one mass on it, this spring stretches some distance e. What happens if I put two identical springs one after another? Well, if I put the same weight on it, this spring up here is going to stretch a distance of e because it has the same force on it. And this spring down here is going to stretch a total distance of e because it also has that force acting on it. And so the total distance it stretches is 2e from where it was at equilibrium, from here down to here. What does that mean about our constant here? Well, in this case, when I have two springs attached here, I get twice the displacement for the same amount of force. What does it mean happens to my constant k? My constant k here, think about it for a brief moment, same force, this doubles, I'll do times 2. So what must happen to k? Well, if this is constant, k, as you might be able to figure out here, is divided by 2. So if you put springs in series, that is one after another, you reduce the spring constant. Generally, the formula for springs in series is this. 1 over each of the spring constants, you add those together, and the sum of those gives you 1 over the total. So in this case, 1 over k plus 1 over k, I guess I should write it out. We get 1 over k total, I'll just write it as k sub t, is equal to 1 over k, if one of the springs is k, plus 1 over k, where k is the spring constant of the other spring. And you can very quickly say, oh yeah, this is going to be equal to, if you add these two together, 2 over k, which is equal to 1 over the total spring constant. So the total spring constant is the reciprocal of that, which is k over 2. It also works if the two spring constants are not identical, although I don't have a really good proof for you for that. If you've got different spring constants, you just plug them in for each of the springs you have in series, that is one after another, add them all together, all the fractions, take the reciprocal to find the total spring constant for those springs in series. So what happens if you put them side by side? We call that in parallel. Well, in this case, this force stretches this spring down by a factor of k. What happens if you hang this on two of these? Well, the force on each one of these now is only W over 2 because it's experiencing half of the force. So what's going to happen to the stretch? Each one of these springs is only going to stretch half as far as it did before, or in this case, 0.5 e, where e is the distance it stretched here. If you think about F equals negative kx, if the same force stretched it only half the distance, what must be true about k? K in this case must have doubled. It must be 2k. What's the formula for springs side by side or in parallel? It turns out you just simply add the spring constants. So if I've got two springs with constants k next to each other, I just add their constants. K plus k gives me 2k. This also works if the constants aren't identical in each spring. You simply add them up and solve it. This is one of the trickier ones. What if you've got something like this where the two springs are in this orientation? Are these in series or are they in parallel? Excuse me. And the answer is, ironically, they act as though they are in parallel. You're like, but they're attached, sort of end to end. Well, not really. In this case, when you move the cart, it compresses or stretches both springs by the same amount. And so it's 2k in this case. Finally, one last little piece. What if you have springs both in series and parallel? If you look at this one up here, these two springs are in parallel, and then that in turn is connected in series with this one. Which equation do you use? And some of you may have guessed already, you actually do it twice. First of all, you do those two springs in parallel. Oh, there's the school bell. If you want to reminisce momentarily. Feels like you're back here. Those two in parallel is equal to 2k. And then you put that in series with this spring down here. And remember, when you've got it in series, you do this. And I don't know if I solved this or not. Oh, I didn't. How would you solve it? You would do common denominators, 2 times 2 over k. So my spring constant in this case would be 2k over 3, or 2/3 of the spring constant of one of them. Hopefully that makes sense. We've got a brain break. Put the same 4 or 5 letter word in front of each of the 4 words in every row to form 4 other common words or phrases. To prevent oversimplicity, the last 3 words in each row are printed backwards. Oh, no! So something blank fall, and then this one right here, sock. And this one, breaker. Oh, I've got it. And this one is, I can't even, chimes. Oh, chimes. Okay. Yeah, I got the first one. It's windfall. It means we got a lot of money. A wind sock is used for measuring wind direction. A windbreaker is a type of coat. And wind chimes, of course, you know. All right. I'm going to count down to 5. If you want to give this a quick try, and trust me, it's worth spending a few seconds just to take a break from the physics and everything else. Pretend you're here. And see if you can find the other 3. I'll show you the answers in 5, 4, 3, 2, 1, 0. Benchmark, shoe, tree, match point. And I got to even think about what the other words are backwards. All right, I'll let you do that. One of the questions is, how does amplitude affect the period of a simple harmonic oscillator? In other words, if you move a mass spring oscillator and stretch it further, what happens to it? Well, remember, oh, I got a little video.
The differential equation is solved by the time-honored technique of guessing.
Warning, this is a Caltech video. Yes, they assume you know calculus. Just watch it and enjoy without worrying about it.
Someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion. So the idea of guessing a sine function seemed quite natural.
Unit circle.
In this case, a sine function with amplitude A and angular frequency omega.
Don't worry, we'll talk about this again
But
in
if
just a
that's
second.
x, is its second derivative equal to minus k over m times x?
This is before the TI Inspire.
The answer is yes, if omega is chosen correctly.
For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant. The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x.
So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians per second. There are 2 pi radians in each complete cycle.
Just a real quick note, how does amplitude affect period? The answer is it does not. The frequency of a simple harmonic oscillator doesn't matter how hard you pluck the guitar string, it still has the same frequency, or how hard you hit a piano key. Just a real quick story before we move on. Who was the first person to realize this? It was Galileo. He was sitting at church in Pisa and noticed an incense burner that was swinging back and forth. Timing the period of that incense burner with his heart, that's the only timing function they had at that point, he discovered that its period of oscillation remained constant, even as its amplitude got smaller. What did this lead into? The invention of the first clocks. Just real quick, an object moving in a circular motion like this, if you just look at it in one dimension, just in this case the vertical direction, you actually end up with the position of a simple harmonic oscillator, where it seems to go slow at each end but fast when it's right in the middle. And so you can convert one to the other. And not that it's critical, but it leads us into this idea. You can actually write this in terms of the equation you saw in the video. The position is equal to the amplitude, that's how far up or down it ends up going, times cosine times omega t, where omega is equal to 2 pi times the frequency. And you can very quickly come up with this graph. And you may have seen this already in your Alg 2 class. Usually when you're working with curves, you play a little bit with it. You can write it either that way or that way. So real quick note on this one. A mass in a spring oscillates back and forth with simple harmonic motion. At what points during its oscillation is it moving the fastest? When it's out at these points here at maximum or minimum is when it's got its maximum displacement. Where x equals 0, that'd be right here. Or the speed is constant. And the answer is, when is this moving the fastest? Actually, when it's passing through these equilibrium points. Right here, here, and here. It actually stops briefly at each of these points here as it stops and turns around before it goes back. You can, if you use a little bit of calculus, you can take that equation we had. And no, I know you don't need to know calculus for this, but I just want to explain where it comes from. If you take the derivative of this, or the change in the position with respect to time, turns out the derivative of cosine is negative sine. You end up with this, and this is a constant, moves outside of this. And you can come up with an equation that looks like this. These equations are given to you on the AP formula sheet. You don't need to memorize them or learn how to derive them, but it's kind of useful to sort of see it. For those who in calculus, you can probably see it. You move the constant out front of this again, and you end up with this constant squared, or that. Those are the big three equations. Now, there's something interesting here. If I take this equation here and put the amplitude back over this side and rewrite it this way, you might notice that this part right here should look vaguely familiar. That is exactly equal to this piece right here, which we know is equal to x. So you can actually write it this way. And because this term doesn't vary with time, you can actually rewrite it just like this. The acceleration of a simple harmonic oscillator is just equal to negative 4 pi squared f squared times its position. When do you end up with maximum acceleration? When you have a maximum position. If your displacement from the equilibrium is 0, your acceleration and restoring force is also 0. Real quick, yes, because we know that this equation is true from the previous chapter. Remember this from circular motion? You're like, no way, what? Yeah, it has to do with this chapter. You can rewrite those three equations this way, which makes it look a little bit more elegant. Some people, and that's why the Caltech video wrote it this way, it just makes it look cleaner. It's the same equations, and you can also rewrite this last equation. Acceleration is simply equal to negative omega squared x. Which way is better? The answer is whichever way you feel more comfortable with. Just remember that omega is equal to 2 pi f, 2 pi times frequency. Another question I can ask you real quick is, if you've got an oscillator, here's its position versus time, what's the maximum velocity and acceleration? Well, of course, in this case, if you look at this, what is the maximum value that the cosine function can have? Well, it's either going to be 1 or negative 1. We're interested just in the magnitude of that, so just 1. So the maximum possible displacement is equal to a. But what about velocity? Well, if you look at this, we've got the sine function here. What's the largest the sine function ever can be? Well, when this is equal to 90 degrees or pi over 2, it becomes 1. And so the maximum velocity of a simple harmonic oscillator is just equal to this term in front, a times 2 pi f. Yeah, I dropped a negative sign because I'm only interested in the magnitude. And what about the acceleration? Well, you might say, okay, yeah, oops, I left an equal sign there. Pretend that's not there for a moment. It's just 4 pi squared f squared times a. When this is equal to 1, and we're just looking at this part right here. Yes, you can also write that as omega a, and this one is omega squared times a, which is why I have them written over here that way. Notice that these are out of phase with each other. When do you get the maximum velocities? It's when the positions are 0. Here I've got the maximum negative. Here I've got the maximum positive. When do you have the maximum accelerations? Well, the maximum accelerations actually occur when you've got maximum displacements, but in the opposite directions. When you've got it displaced the maximum positive position, the acceleration's a maximum negative. And it's, again, the idea you've got, this is a cosine curve. I should really start it right around here. This becomes a negative sine curve. And this one becomes a negative cosine curve. All right. Given this equation I gave you just a moment ago, we said that acceleration equals negative 4 pi squared f squared x. What can we do with this? Well, if you remember Hooke's law, which is the single requirement for simple harmonic motion, you replace the force with ma. And if you do that, and then divide both sides of this equation by m, you get a equals negative k over m times x. And you might say, well, why'd you do that? Well, take a look at this equation down here and this equation up here. A equals negative something x, a equals negative something x. If this is true for a spring, and we know all simple harmonic oscillators have to obey this law, we can actually state something. We can state that this constant down here must be equal to this constant up here. In other words, k over m must be equal to 4 pi squared f squared, which means we can rearrange that slightly. Take the square root of both sides. The square root of this side becomes 2 pi f, and the square root of this side becomes just k over m. And rewriting that just slightly, we can solve for the frequency of a mass spring oscillator. The frequency of a mass spring oscillator is just 1 over 2 pi times the square root of k, the spring constant, divided by whatever mass you have hanging on that spring. And because period is equal to the reciprocal of frequency, you can also rewrite that equation this way. And this is the equation that you'll find on the AP formula sheet for a mass spring oscillator. The period just equal to 2 pi times the square root of the mass over the spring constant. And it's very useful in a lot of ways. Take a quick look at this, just a real quick walking away from those equations for a moment. Given our equations down here, if you have this equation for the position of an oscillator is 2 times the cosine of 8 pi t, what's the object's amplitude? Well, if you look at this, this has to fit the form down here. The 2 in front must be the amplitude, and we always work in meters. What's the object's frequency? Well, if you look inside of this, it should be equal to 2 pi f times t. In this case, we've got 8 pi. 8 pi must be equal to 2 pi f. Oh, sorry, it's too slow for me writing on this thing. And so most of you can see obviously what the frequency is in this case. The frequency must be 4 hertz. 4, and again, remember the units for frequency are hertz. And write the equations for the object's velocity and acceleration at any given time. Well, what happens here? The velocity is just equal to negative the amplitude, so negative 2, times the constant that was inside. So that gives us negative 16 pi times sine. And inside of that sine is the same as before. It's just 8 pi t. It hasn't changed at all. Please forgive me for writing so slowly. I'll get this working before the next video. And what's the acceleration? Well, the acceleration then is just negative, and that times that again, 80, 40, oh, I hope I got this right. Negative 128 pi times the cosine of 8 pi t. Sorry, I'm still double checking my math in my head. I think I got it right. Please forgive me if I didn't. Let's see. 2 pi f 8. Oh, I forgot my pi squared. So sorry. Negative 128 pi squared cosine 8 pi t. Should be correct. 80, 48. Yeah. Okay. Phew. Take a look at this conceptual question. At what points during its oscillation is the magnitude of the acceleration of the block the largest? And hopefully you'll remember that that happens when it has maximum displacement, but it's negative. Oh, we got another brain break? Holy smokes. Spell 5 7-letter words with the help of these scrambled letters. All the 7 words begin with the letter P and end with M. What are the 5 words? Oh, gracious goodness. I'll wait 5 seconds. I can't solve the first one. It's driving me crazy. Yeah, I'm countdown 5. Again, pause the video so you have a chance to try a couple of these. But I don't want to hold you up. I'm going to count down 5, 4, 3, 2, 1, go. Phantom. Oh, duh. Perform or preform problem premium pilgrim. All right. Springs in simple harmonic motion, just a quick note on this one. When you have maximum displacement, when this x is equal to a, you get a maximum acceleration, but in a negative direction. When it's at the equilibrium position, when x is equal to 0, the acceleration is 0, and you get a negative velocity maximum. Here, when it's at its, the x is equal to negative, the amplitude, velocity is 0 briefly, and the acceleration is maximum in the positive. Back here at equilibrium again is velocity 0. Velocity is maximum, the acceleration 0. And then back when it's back here again, we repeat that same sequence. And you end up with this situation where the potential energy and kinetic energy keeps oscillating back and forth. As it stretches out, you get maximum potential, no kinetic, and then as it swings back down again, that potential gets converted to kinetic again. We know the total, the total energy actually should be the sum of the kinetic and the potential. In other words, 1/2 mv squared plus 1/2 kx squared. And we know from earlier that we've got this equation for x and this equation for velocity. Therefore, if I plug them in, the total energy should be 1/2 mv, this is this term right here, squared, plus 1/2 k times x, that's this x right here, squared, at any given time. The multiplication becomes ugly. You end up with this. And now, how do you simplify this down? If you remember that from other slide that k over m must equal 4 pi squared f squared, if I substitute that in for that term right there, I get this. And then if I take this equation here, notice that m's cancel. So I end up with this. Factoring out the k's on both of these, you might recognize, oh, wait a second. I can factor out the a squared out of both of these. And then I end up with sine squared of this plus cosine squared of the same thing, which means sine squared theta plus cosine squared theta is equal to 1. So the total energy of a mass spring oscillator is just equal to 1/2 times the spring constant times its amplitude squared. That is a very useful equation. Now, going back to the other idea, we can actually use this now to solve it. The total energy is just equal to 1/2 Ka squared, and that's equal to the kinetic energy plus the potential. So take a look at this example problem. A 1 kilogram mass is connected to a spring with a spring constant of that. Its amplitude of oscillation is 0.5 meters, and its frequency is that. What's the velocity of the mass when its displacement's this? So not all the way to the outside edge. So this is dealing with a distance, which is exactly what I have up here. So to solve A, using this new idea here, we know the total energy is 1/2 Ka squared, amplitude was 0.5, equals 1/2, that's mass is 1, plus 1/2 the spring constant, and I want to know its velocity when its displacement's this. If you solve this, and if I solved it correctly, you should end up with that velocity. Now, part B here, what's the velocity at this time? Now, this equation up here doesn't involve time, so how in the world am I going to solve B? And to solve B, I'm going to use some of our old equations. This one, the velocity is negative a, and just plugging it in, the amplitude, the frequency is 1. Multiplying, I'm trying to figure out what's velocity when time is 2 seconds. You'll discover that the velocity is 0. Warning, when you solve this, we have to be in radian mode. So the sine of 4 pi should be 0. Check your calculator. For this chapter, we don't want to be in degree mode. We want to be in radian mode. You can also take that equation we just had, and you can actually solve it for the velocity. And so you can come up with a more general equation. We did it by solving the whole equation, but in general, this equation is also always valid. K over m, spring constant over the mass, times the amplitude squared minus the displacement at any given instant gives you the velocity at that instant. All right. And our next piece, or the next day, you've got a little lab dealing with simple pendulums. I'll explain that later. Have a great night. Good luck with the homework and worksheets. Look back at the video if you need to. Talk to you soon.